So you are able to see the screen, right?
Yes, sir.
So anyway, so last
Yes,
class,
sir.
okay. So last class, so we have seen our this one. Yes. So we have seen, you see, of these principles of stratigraphy. Okay. So like looking at a cross section, say, we have to now tell the entire geological history of that place itself. Okay. So for that, we have seen there are some type of rules are there, which they call Steno's laws of this stratigraphy. Okay. The same thing only I'm just putting out. But I think I forgot also maybe the most important thing is this Steno's rules say that will give only relative ages. Okay, so like you see the top one is young, the bottom one is maybe older than oldest, like that. But this stratigraphy rules they will not tell you like how much old it is actually. What is young means young means 10 years or 10 million years, so that will not be known, but relative ages of rocks can be decided based on these rules. Okay, so this was the rule, original horizontality. Like we have said, all rocks when they form, say, they will everything will be horizontal. Okay, until maybe they may be tilted by faulting or maybe something else may happen, and that inclined things may come up also. Then lateral continuity also we have said. So layers are originally deposited, say. So later on they may be faulted or maybe erosion may happen after their deposition. Then superposition also. So like you see older, younger, the principle of superposition. The top one will be young and the bottom ones will be the older thing. Then cross cutting also we have seen. So if you have a dike or sill, say, so we say that it is younger than the rocks, basically. They cut across. So this is what we said. Then fragments of rocks is contained in another rock are older than the layer they are contained in. Then of course the last one we have, of course this doesn't come under stratigraphy. Later on it has been added. That is a faunal succession. That is based on the fossils also. We can date, you see, the ages and other things also. Okay. So this also I showed you. So this figure say, so this second one. So one is here. So these red rocks say are older than this yellow inclusions, yellow rock, these red inclusions. Okay. So that comes based on this inclusion kind of rules itself. So these rules, if you follow, say, so you should be able to, tell the, you see, what is young, older, oldest, and then you should be able to explain the geological process, what has happened in that area or how things have evolved in that process. So these are very fundamental things also. The same thing I'm just showing here, the same rules say. In internet, you will find many, videos or many informations are there, So you can say, so this is a superposition, say, that is younger up to the oldest. Then the dike, say, so this has cut everything. So this means this will be more younger than the remaining thing also. Then you can see original horizontality. So previously everything was continuous, but this river has eroded basically this entire the region itself. But then still the properties here and here they will be same also, like cross cutting, and these are inclusions. These green color things, they are all inclusions from the below rock, so they will be older than this the layer where they have been deposited also. So these rules you should be able to explain any geological process by looking at a cross section. Okay. And now unconformities also I told you last class. And then we have decided unconformities, some three are there: angular, disconformity, and other things also. But the most important thing, what is that unconformities? Yeah. So can anybody point out, like last class, what is the most important thing about unconformity? Yeah. See, what is meant by unconformity? Like last class I told you, right? What is the speciality of these unconformities? Yeah, we have said in the last class, right? What is the speciality? Like unconformities, what did we say? Yeah. So you can see here angular unconformities, we say like below layers are inclined, the top ones are horizontals actually. Okay. And then disconformity means all layers are horizontal, like perfect linear kind of thing. Then suddenly you will see a wavy type of a structure. Or you will see like sedimentary rock deposited on this top of igneous rocks, and then this thing is also wavy kind of a thing you will see. That's what we are calling as non-conformities. So the speciality, what is the speciality about unconformities? Like last class I told you, right? What is the main speciality? Or what does that tell? When if you have found out unconformity, say, so what does it tells you? What it tells?
Something must have happened, something extraordinary.
Excellent. So something extraordinary, because everything has to be continuous. Okay, non-conformity itself is something like a discontinuity kind of thing. So like you see this here, if you see igneous rocks, metamorphic rocks, they will be extremely old rocks. Sedimentary rocks will be very new. Say like for example, the top layer is 50 million years, say. Bottom one is some 500 million years. So from 500 million years rocks you are having, on the top of it you are having only 50 million. So there is a huge discontinuity. So generally we expect after 500, so you may have some 200, 300, sorry, 300, 200, 100, like that. There has to be some kind of a continuity. But here what happens is, some huge discontinuity. So this is what we call as unconformities, and they're very important, for the geological time scales also. So like here also, if you see the top rocks, when they do the carbon dating or this one, so the upper layers are extremely young basically. So they may be like you say 25 million years or 50 million years, and below some 500 the million years. So between them, you don't have like a continuous thing. So that means something has happened basically in between these two, or maybe before the younger rocks was deposited, say. Yeah, definitely there could have been 100 million years that rock will be there, but something has happened, like some erosion or maybe some volcanic activity or whatever. Something has happened, and suddenly these after some lot of time, then the younger rocks were deposited. So this is a very important thing in classifying our geological timescales also. So this also we have seen in our last class actually. Now the last principles which has been added, like principle as a faunal succession. Okay, so this of course this comes into paleontology and others also. Right, in 10 million years back, some specific organisms were used to be there. Like that, slowly, each time say you will have special organisms are there. So based on their carbon dating and based on their fossils, you can say. So like for example here, so the first one is the oldest layer. So here you will see these type of fossils actually. So once you go up slowly, 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 slowly. So once this era has ended, say, then sediments get deposited, and during that time, what type of organisms are there? Say, so their fossils will get deposited. So like that. So now when you do this, so if you want to find out the age of the rock, say, so if you can find out the age of this fossil, automatically you will know, the geological history, what would have happened, in that region also. So this is also very important. Like you say, so let us say this is a type of rocky material you get in one area, say, and this is in some other continent or some other place. So if you want to date, say, so now you can say that the structures are entirely different. But if you go by the fossils, say, you can see 1, 2, 3, like this middle one, say. So same type of fossils are happening in this range also. So now you can say that the age of this rock and age of this rock, both of them are same. So something like that. You can make some kind of conclusions also. So this is also one very important graph. You can see this is one area, and these two are miles away. Means they may be some other continent. This may be in India, and this may be in Australia also. Now when you date, say, so based on the fossils, basically you can see this type of fossil is not available here. So this comes under one, the oldest one. Then comes the second. Now you can see the third. This fossil is observed in both the layers. This means these two, this rock and this rock, so they belong to the same geological time actually. Then after that you have four. These two are same. Then on the top of it, so you have this type of fossil. Now, but in this place you are having this fossil occurs on the top. So these two belongs to one time group of time, and this may be older than this one. Then you can have 7, then you can 8, like that. So this also we can classify the relative ages basically, like which is old, which is younger. So this also we can get from this faunal succession also. But this you have to do a lot of paleontology, anyway we will not be doing. So like you see these are fossils, how do we carbon date them? So all those things comes into picture. So this is also very important in our this the stratigraphy, okay, to classify the ages of all the rocks, relative ages basically. Okay, and now relative. So the Stenos laws of stratigraphy say they will tell you only about the relative age, like which is younger, which is older, which is the oldest only. But if you want to know the absolute ages, like the top rock is 10 million years, the bottom one 20 million years, 30 million years, 40 or 50 or 100. So then if you want to measure the absolute age, say, so this radioactive decay, it has become very popular basically. Okay. Now, can anybody tell me radioactive decay? Who started this type of work, like radioactive decay, radiations? Hmm. So, who got Nobel Prize for this radioactive decays? Any of you know?
Madam Marie Curie.
Marie Curie, excellent. Okay, so she started. So after her work only, the whole this geological subject, it became very easy, and people started a lot of applications actually. Okay, so they gave Nobel Prize. She found out only radiation, but then people were not aware. Then the people started using for all the things. It is used not only for dating of the rocks, even skeletons, fossils, everywhere. This carbon dating has become like a standard kind of thing. So this also I told you in the last class. Generally, when the materials are formed, say, they will be unstable kind of thing. I hope all of you know, right? This is C12. So carbon 12 means, that 12 tells you six protons or six neutrons kind of thing. So they should be same actually. But if they are not same, so like C6 and 8 are there, so six protons or 8 neutrons or whatever. So that creates some kind of unstable and radiation starts. Okay. So these are all these unstable materials. They will collapse to a stable material. So they call this as a half-life actually. Like how many atoms, half of them will become stable, like initially all are the unstable, but half how much they will become stable. This is what they call as a one half life actual. Okay, then two half lives is there. So they follow this type of an exponential law, and this is very well established. So this is what they say, like uranium, last class as I showed you, finally everything comes down to lead only. Okay, but the one half life of uraniums, like half of them to decay, it takes 4.47 billion years. Then uranium 235 is 710 million years. Then potassium is 1.25, rubidium 50 billion. Then carbon 14, which is carbon 12 is stable, but carbon 14 is not stable. And finally it converts into nitrogen 14. Its half life is 5,730 years. So generally, if you want to zircon, oldest type of a rock, found in an earth, then igneous rocks is to do carbon dating. They use this, this uranium 238. They will find out this age, this material. Then if you want to date a volcanic rock, say, the potassium things will be more. So based on that, you can find out the rocks. And of course, igneous metamorphic, this also they use rubidium to strontium. But of course, as I already told you, half-life itself is 50 billion years. It's a huge. It is much older than the Earth itself. So carbon 14. So this has 5,730 years. So this is a widely used for organic materials, plants, fossils, and others. Coal, bone, everywhere. This carbon 12 is used basically. Okay. Now what they say is the argument is this carbon 14 is a unstable element. It locates in our Earth's atmosphere. So it seems it enters our plants, and then we also eat, we follow it. So this also we also radiate some this one. So due to this, they find out this carbon dating also. So this carbon 14 routinely, but the only thing is because the lifetime half life is small, you can date only the recent kind of things itself. So this is the one which they use to find out absolute age of the rocks also. So this is a geological time scale, of our Earth. So that trend is, so about around some 4.5 billion. You would have seen that James had a lecture also. Okay. So they say our solar system or whatever things they have formed some 4.5 billion years ago. So from 4.5 to 6 billion years, say, around during that time. So the whole region, say, this is the current region is here actually. So it is something like one 360-degree circle if you take, say, coming from the past to the present basically. So these entire things, what they do, geologists, they divide this into some kind of, times, geological times. Generally, time, for us is, 24 hours, 365 days, the seconds, minutes and other things we use, all are equal intervals kind of a thing. But geological time scales are not, equal intervals. They will be unequal in length actually. So like, for example, Hadean, say, this is the oldest, this one. So its length is 4.6 to 4 basically. Then we have Archean eon, we say. So it starts from 4 to 2.5 like this. There are unequal sizes. So so this is what they said. So these time intervals are not equal in length. Of course, the time intervals are variable length. Each thing has a different sizes basically. So because the geology, these when this time the length of each interval say. So they find out from some major geological thing should have happened at that time. So if something has happened here, say, so that ends one of the era or one of the eon of that thing itself. We will see this also. So that's what. So the geological times, it is based on history of Earth actually. So how Earth was, there has been a major geological change in the whole Earth, say. So there, they draw one line and then say that era, that place has closed, and then they move into the new eon or other new time scale starts itself. So this is one of the Earth say. So generally, although Earth was 4.5 billion years or 4.6 billion years old, so people recently, they have found out in Australia or something, stromatolites actually. Okay, so this is a fossil. It has like something like a microbial thing itself. So they have found out this type of a stromatolite whose age is 3.5 billion years, or maybe four. Very huge old this itself stromatolite. This is one of the, you can see, the microbial things actually. So you can see now also these stromatolites in oceans, it is like a coral reef kind of thing itself. But of course, these are all very young. But one they found out in Australia or some other place, which the age is, some 3.6 billion years or something like that. So this is one of the oldest, that is a microbial thing, which started, they say, which led to all this life and other things. We also have evolved from this thing itself. So now this is a very important thing because, when you are doing planetary geology, say, like astrobiology, as already mentioned you, this is, of course, this also tells us about the ages of the rocks also. But at the same point of a time, so when you're going for planetary explorations, like, I showed you Mars or other, icy moons or whatever. So this type of organisms are there, so microbes or something, one can say, like these microbes, they started producing oxygen, and then that is how the entire geological time history started also. Okay, so this is the oldest, you can say, microbe or which has been formed on a stromatolite. Okay, so now these this is a geological time scale. So we have eon, era, period, and epoch itself. So now I will explain you what is eon this itself. So epoch, if you see, so epochs are smaller time scales basically. So now all the boundaries say, like, 250 to, like, today 11.8 something, Holocene Pleistocene ended and Holocene started. So all these boundaries say, so they tell us some important geological event. So can anybody point out 66 million years? That is from Cretaceous to this, Paleogene. What is this boundary corresponds to? Yeah. So 66 million years. What has happened? What this geological boundary indicate? That is from Mesozoic to Cenozoic era. Now, what is the most significant thing happened on Earth? Any one of you know? See this boundary from Mesozoic to Cenozoic era. You can see the words here. In Mesozoic, we have three things: Cretaceous, Jurassic, Triassic, actually. So at 66 million years ago, say, so they have put a boundary, geologist. What has happened during that time? Now, why they have put a boundary there?
The Jurassic Era ends.
Now, what is the
Dinosaur
Jurassic
were
era?
extinct. Dinosaur became extinct.
That huge impact, you remember that, some impact occurred, you would have studied also, like, the whole earth. Of course, some people said it's a meteorite impact, some people say volcanic activity. So during that time, say, so everything got vanished on earth, and new geological era started actually. Then around 252 million years, say, that is from Paleozoic to Mesozoic era also. So around 252 million years also, in geology they have found out the fossils. So what they have found out was, around 252 million years also, 90% of lives on earth was under extinction actually. The plants, genes, everything, some huge geological process happened at 252 million years also. So like that, you see, so all the boundaries, say, of our geological time scale, they have some significant thing which has happened at that point of time itself, like, Phanerozoic eons, say. So Proterozoic to Phanerozoic, say, life was microscopic kind of thing. Cenozoic means, you see, the new life kind of thing. So they have some Greek names or something they have borrowed. So the Cenozoic era. So now all of us are living in Cenozoic era, then the Quaternary period, and in the Holocene epoch itself, actually. Now geologists also have started telling now recently, like human beings, we are also changing the, Earth planet itself because of this, whatever you can say, like, you see this, we are also having that green, petrol, followed, right? Pollution, dilution. Now they are trying, there is under debate actually. So after Holocene, they wanted to add one more epoch actually. But this boundary from the Holocene to the next epoch, Anthropocene or something, they wanted to add. But this boundary has, basically made by human beings only. In the whole world, we are using, right, all fuels and other things are happening. So all the boundaries in geological time scales, they tell us about, the very important geological process which has, done occurred during that time itself. Okay, and this is also like the geological time scale. Of course, this is linked to paleontology also. Like, you see, during this time set. So we had a dinosaur time. That's what I told you, Cretaceous, Jurassic, Triassic time. So all of them got extinct actually. So then automatically, this quaternary tertiary started like that. They create all these type of boundaries also. So now, so that's what we told. So the boundary events is whenever you say a boundary in geological time scale, that means some global extinction or something huge things have happened basically. So that's what I told. So the boundary between Permian and the Triassic actual. That means this region that is around 252 million years say. So there was one mass extinction basically, which has happened during that kind of a time, and they say 90% got eliminated or something. Now, another boundary is a Pre-Cambrian and the Paleozoic basically. So Pre-Cambrian is here, that is a Proterozoic and Paleozoic. So this is a boundary. So these three, say Proterozoic, Archean, Hadean, so they also call this as a Pre-Cambrian era. So here also there was a transition basically. So the first, this appearance of animals with hard parts. So previously it was all bacteria, some microbes was there. So this also like, so all these things indicate some significant geological process. So here in the geological time scale, the first one is eons people use. Eons are the largest intervals of geological time, okay, and 100 of millions of years in duration. So these are very broad kind of a scales basically. So in the time scales, you can see the Phanerozoic eon is the most recent and began more than 500 million years ago. So this was the thing, okay. So you can see the eon is the first column you can see here. So the whole geological times is divided into 1 to 4, the eons basically. So Hadean, Archean, Proterozoic, Phanerozoic kind of thing. And the Phanerozoic is a recent one, and these are the oldest kind of eons. So the sizes are huge basically. You can see this graph. So you can see Hadean eon is there, say. So this Archean eon, then Proterozoic eon, then these are one more eons actually. Okay, so these three eons basically. So now the recent one is very, very small, but these are all the old things itself. So eons are huge time scales. Then we have eras basically. So eons are further divided into eras itself. So eras are like this, okay. So this is eon, 4 eons are there. Now this is a Phanerozoic region, say, because what has happened in the olden days of our earth, you would have seen Professor James Head's lecture. He would have told you, right, the old history, we don't know much information about these 3 eras actually, what has happened, these eons, sorry. But we know most the whatever we know, say Phanerozoic eon, we know some more details. So because some more information, say what people geologists have tried is they divided this into further 3 regions itself: Cenozoic, Mesozoic, Paleozoic. So this is what they call as eras actually. Okay. Then this eras is further, they divide this into periods basically. So these periods also will come into this one. So like for example, so here Paleozoic, Mesozoic, Cenozoic, these are the eras. Now Cenozoic eras, once again we divide this into periods. So Quaternary, Neogene, Paleogene, or Cretaceous, Jurassic, Triassic, further they have been divided. So periods are much more smaller itself. And then, the next one comes is epochs actually. So this is what we use. So once again, finer subdivisions comes into picture. This is what they call as, the epochs. So this also, because a lot of information came, say carbon dating, that became very popular. People started using this carbon dating, so a lot of rocks have been found out based on those things. So once again, they divided this into further, the epochs itself. So in our geological time periods, we have broad scales that what we are calling as eon, E0, EON, okay. Then we have eras, then we have periods, then we have epochs, and now people are further dividing epochs into another small time scale. They call, I think, ages or something, like that also. But please remember that all these boundaries say. So they tell you about one the it is like a huge kind of thing, some huge extinction or something has happened basically, which the huge geological process got altered or something like that only. So now in our earth, when you do this carbon dating, so what is the oldest the mineral on earth? That's the oldest like you see, when earth was formed, so it was also like lava kind of thing. It was extremely hot because of lot of the bombardment happened, right? That all the small materials, you see, they started bombarding each other, and then you see they joined and then formed this planet. So when our earth was formed, so it was extremely hot actually, full of lava kind of thing. Then slowly things got solidified and then rocks have formed basically. So if you see in our earth, say The oldest known mineral, that is around 4 billion years, or something 4.2 billion years, is this zircon actually. So this is a special rock. Of course, zircons are there at many places, but they when did this carbon dating, say in zircon somewhere in Australia. So it was showed that it has the age of 4.2 billion years. So this is one of the oldest kind of a rock which was formed during the Archean era or Archean eon, in the olden days itself. Then in Canada also, so people did this one. So this is like Augusta Nice actually. This is also a stone. So the age also they found out was something around 4 billion years old. So one of the oldest rocks, which have been formed on our planet Earth also. Then how do they find out the age of Earth? Say, like you would have like 4.5 billion years they are telling. Okay. So how these geologists, what they did was, right, how Earth was, all the planets, how they formed was impacts only. Like you say, as last time also I told you, that interstellar cloud will be there. Then slowly the things starts rotating, and then all these small asteroids or whatever the particles they hit one another, and then you see the planet forms. So impact cratering only creates all these planets. So to find out age of Earth, say, so this was a meteorite actually. So these meteorites are the these things. The one meteorite has collapsed on Earth long back. So I think somewhere this one. So they carbon dated this meteorite actually. So the age of this is also something around this 4.5 the billion years itself. So that's what So to rise, so the oldest Earth rock, whatever we have found out on rock, is in around 4 billion years. And of course, the radioactive decay has been used. And the oldest earth mineral, so that is at zircon. Okay, so this oldest earth rock is this one. That is this actin is, and this zircon is the oldest mineral. So if you do carbon dating, say, it turns out to be 4.3 billion years. Then Earth's mantle and crust, say, people have done some. Our Earth is also like a nuclear reactor only. So inside they have done some measurements, and they say that 4.5 to 4.55 billion years. And the oldest meteorites, their age is also around this one. The oldest moon rock, because Apollo, the astronauts went and then brought the rocks, and they were carbon dated, and their age is also 4.45 billion years. And sun's age also, some theoretical calculations are there. So based on these things, this one now when Earth has been formed is 4.2 billion years. So that argument, that hypothesis was brought out actually. As already I told you, right, in geology, if you make any hypothesis, you should have analogies, and then you should have some kind of a reasoning. So people have found out like what is the age of Earth. Hypothesis is 4.5 billion years. Now how do you support your hypothesis? For that, people have done all the calculations like oldest rock, earth mineral, crust, meteorites, moon rock, sun. They have got all the analogies, and then finally the conclusion is 4.5 billion somewhere around that time Earth originated, or our age of the solar system also. So this is what people use. So this is what I told. So these eons is 4 eons are there. These are the broad time scales: Hadean eon, Archean, Proterozoic, and then Phanerozoic. Now these three combined say, so these are, they call this as a Pre-Cambrian basically. Okay, of course Phanerozoic is known as a Cambrian. Before Cambrian, Pre-Cambrian comes basically. Okay, so you can see, so if you see the whole Earth geological time scale, so this is a Phanerozoic, where we are in that eon right now. It has only 12% of Earth history. The Hadean eon, Archean eon, Proterozoics, they contain almost almost how much it is, 88% of our Earth history is contained in these eons only. But in these eons, so the information available to us is very limited. So like that James Head lecture you would have seen, right? He would have said, no, only we know hardly 12% or that much only we know, but we don't know, we don't have information say about these eons. We don't, of course we have some small fossils or some small rocks at some very few places, but we don't have like a strong the evidences like how these boundaries formed, what has, how Earth shaped, or how Earth evolved. Say that information is not available. Okay, so this Phanerozoic is when where we are there only 12%. The remaining things we know only very few information. Okay, and now, as already I told you, the Phanerozoic, that the eons is further divided it into eras actually. Okay, of course, you don't, this we cannot divide Archean or Proterozoic, so we have no idea, Hadeans, whether you can divide them into eras, because information is much limited. Only the Phanerozoic, because we have information, fossils are there, ages of the rocks are there, so this can be divided into 3 eras: Cenozoic era, Mesozoic, and then Paleozoic. So the names are like old life, middle life, new life kind of thing itself. So all of us are, we are located in Cenozoic era. Okay, and if you tell eon, Phanerozoic, eon kind of thing. So that's what they say. So the boundaries also has been decided. Paleozoic means some trilobite, something, land plants came up. Then age of dinosaurs. And Mesozoic is age of dinosaurs, we say. Then Cenozoic means, the age of mammals. So from paleontology, also, these names came into picture. Now, eras say further era can be divided into three groups actually, like Paleozoic, Mesozoic, because we have a lot of information, the geological process. Still, you can divide. So Permian, Carboniferous, Devonian, Silurian, Cambrian, Ordovician. So like that it comes. So this also indicates maybe based on paleontology or mammals, or you follow it, the fossils and other some geological things. Further, this has been divided also. And once again, say eras actual. So you can divide it into periods. That is a Quaternary period, Miocene period, Paleocene, these things. So the recent one is Quaternary. That is where all of us are living in geological time. So once again, as already I told you, the smallest thing is epochs actually. Okay. So eon, from eon you came to era to period, then period to epoch basically. Okay. So this is a Holocene. So this is where all of us are there itself. Okay. Now, of course, that's what I told. Right? Since humans are having notable impact, say, so they say that nowadays people have started quaternary, because we have modified the earth, the geological things we followed. So because of humans, many mountains, lakes have been getting filled up, and lot of pollution. So many things have happened. So now geologists are trying to add one more after Holocene, say, Anthropocene, some kind of a era because of human beings, industrial revolution, say. Of course, the whole planet's geological process, it has a significant effect. They wanted to add one more in our epochs also. Of course, there is a discussion is going on, but till now we have come to epochs. Now epochs also have been divided into some small things. They call as ages also. That is how the geological lifetime, these time scales have been evolved. So this is just a summary. Okay. So eon, then era, then period, then epoch. After epoch also we have ages also. Like that, it goes into small intervals also. Okay. So this is the geological, the time scale, which is given by Geological Society of America. It is frozen actual. Like I told you, right? Eon, then era, then period, then you can period ages also, epochs will be there. Then you can once again ages also. The periods also have been divided into small things, ages also. So like that, it goes into pictures actually. So all these boundaries is whatever you are showing, whatever you are seeing in this graph, all the boundaries, they are not like unequal intervals only, but each boundary will tell some significant geological thing happened during at that point of time itself. So geological time scale means eon, then era, then period, epoch, and ages kind of thing. It goes based on this one. So now this is our geological map of India actually. Okay, done as per the ages of the rocks, as per the things. So you see how they use here. What is the youngest thing? Can you read here? Yeah, so you can see this help also, like a Quaternary, Neogene, you follow Paleogene, Cretaceous, Jurassic, you follow Permian, Paleozoic. These are all the eras, periods, and this one also. And now can you find out here what is the recent one? Recent, where do you see the recent things in India?
Quaternary.
Quaternary is a recent. We are all living. So where is the quaternary sediments or quaternary things where you can see in India?
In Northern Plains.
In
Northern Plains.
In the Ganga Basin. Okay, this is Ganga Basin you can see, right? So these are all quaternary sediments basically. Okay, like in Assam also Brahmaputra sediment you can see here in Calcutta. So all these things are very young sediments actually. You follow? So Uttar Pradesh, if you go, so you can say it is a very young kind of a place. Now after quaternary, next comes these have been arranged as per the date actually. So you can see the next comes a tertiary actual. Okay, then comes a Jurassic kind of thing. So where is a Jurassic kind of a thing? Yeah. So which is the region in Jurassic here in our India?
Maharashtra.
Maharashtra. What do you call this one in geology? Famous word they use, no? This blue, entire green color. What do they call? The famous name for Maharashtra. These regions, what do they call? What do they call? This is a very famous name is given to this. They call this green color as Deccan Traps. Any of you have heard this word, Deccan Traps? See the Deccan Traps, have you heard? None of you have heard this Deccan Traps word, geology. See, what is the speciality of Deccan Traps? Any of you have any idea? See, these Deccan Traps have been formed during what time? You can see here, they have been formed during Jurassic this time itself. I don't know how many of you are reading, the scientific journals, geological journals. If you say this Jurassic time, say what will happen during the Jurassic time? So here, as already I told you, 66 million years ago, say. So what does this boundary corresponds to? So this Jurassic Cretaceous is there. So this, what did we say? Yeah, previously, like 66. What has happened? What is the most important event occurred here? No, volcanic thing is fine. But what has happened 66 million years ago?
Dinosaurs were extinct.
They were extinct. But how dinosaurs were extinct? See, our
striking of
traps
the asteroid.
No, that is one theory. But another theory was 66 million years ago, say. So dinosaurs got extinct. But people say that, but at the same time, Deccan Traps was formed in Maharashtra also. You followed. So they say that at that 66 million years ago, say, so there was a volcanic activity here. You followed. So these Deccan Traps is all green color, say. These are all lava, basalt, this one which has been formed like this. So these Deccan Traps also formed at the same time. So there are two theories are there. One is due to asteroid impact is there. Another one is during that time, so there was a huge volcanic activity. Even on Earth, India also at many places, huge volcanics, they went and then you see the gases got emitted, ash, and then you see they removed all this dinosaur, Jurassic time itself. Okay. So that is how this is also one theory. I will just show you also. Now after Jurassic, then we have Mesozoic, Upper Paleozoic. And now where are the oldest rocks in India? What is the oldest rock? Where do you see oldest rocks in India? Can you read the last one? So this is a pink color. So what type of rock is the pink color? So that pink color, can you read? What is that? They belong to which period or which eon?
Archean.
Archean means, so if you see this time, Archean means you can see it is a eon basically. It is not in the era or a period or epoch. It is a very old, 2.5 to 4 the billion years itself. So we will see these type of rocks also. Where do you see these type of extremely, the old rocks? You can see mostly in South India, So of course, the South India, Chennai, and other places, you can see these type of rocks basically. Now, can you identify this portion, this small region here? What is this? So people from Andhra should be able to identify this small, you see my cursor, right? What is this?
Kadapa Basin.
Kadapa Basin, basically. So when it was formed, the Kadapa Basin. See, the Kadapa Basin has formed. Previously, it was all pink color. So pink color means Archean rocks, basically. So now if somebody says Kadapa Basin is older or Deccan Traps are older, what is your comment? See, Kadapa Basin, when it was formed, you see the color here? When it was formed, Upper Proterozoic actually. So you can see Upper Proterozoic means here basically. So this is a Kadapa Basin was formed here. Deccan Traps, when they formed, see Deccan Traps formed during
Mesozoic.
the 66 million years. So now you can tell, you follow, right? Kadapa Basin is old or Deccan Traps are old actually. Which are younger here?
Deccan Trap is younger.
Deccan Traps is younger. So now all of you are staying, right? You can see this map and you can now identify actually. So this Utkarsh is from which place?
Sir, I am from Patna, so it is in the Quaternary region.
So you are the youngest in the class actually. You followed. Now this Kshitij is from which
Yes,
place?
Sir, I am also from Quaternary region, Delhi.
I think both of you are young. So we are all Buddha people. You followed, right, in Chennai. Okay. So now, so this is how, you can understand basically. Okay. So now, which is young, which is old, say. So this tells you the geological time scale. So how you should read this map itself. Okay. So now this map is available in the Bhukosh website also. It is a whole GIS format. It is available. Okay. So you can download. I will show you maybe at the end of the class. So you can easily identify, where older rocks are there. You should be able to handle. Okay. Fine. So this is very interesting things. So now this is what we said. So the Hadean eons say. So the Hadean eon, this Archean eon, we don't know much information. So what people, it is just like a speculation kind of thing. So Hadean time, it was like Earth. There was no rock and Hadean time at all. Okay, so it was like a partly molten surface. Only volcanism impacts was happening, and of course, Moon was also formed at that same time. Because for us, plant geology, Moon is also going to be very important. So this Hadean era set. So in Hadean era, there was no rock at all, basically. We followed it. It was all molten kind of thing. Then slowly, you see, it solidified, and then Archean set. So this started, you see, the beginning of the rock record, we say. So if you see our geological cycle set, so there is no rock of Hadean, this one. So rocks started forming in Archean. So this is like a boundary. So Hadean to Archean means, from molten things we have started, crust started solidifying, and rocks have formed itself. Okay, that's the Archean era. Then Proterozoic ions. So this is what they said, right? Is oxygen came up and then you followed, right? In that atmosphere, that microbes or whatever, they started to come. So these are the boundaries basically. Then the Pre-Cambrian era. So the Pre-Cambrian era means combination of these three. That is Hadean, Archean, Proterozoic. So these three consist of what we call as a Pre-Cambrian era. Of course, the Phanerozoic is known as Cambrian, pre. So pre means these three including basically. Okay. So that's what we told. So these three itself, 8 by 9th time of Earth's history said, like in that circle I showed you, right? Out of 9 parts, 8 parts is controlled by this three Precambrian era. Hadean, Archean, that Paterozoic or whatever, this place, Proterozoic actually. Okay. So this is what it controls. And of course, as already I told you in Professor James Head's lecture also, he would have told you, we don't have any information about these three. Only one rock here, there, something fossils are there, but we don't have detailed, informations about these things. So scarcity, we have erosion. We don't have any idea actually. Not much things are. That's why you see people are going to planetary geology, because all the, if you want to know about Hadean era, or if you want to know about Archean era, say, or if you want to know about Proterozoic, say, best thing is you go to Moon basically. Okay, so Moon, because weathering is not there, so that may give some kind of a clue, like how our Earth was during Archean time or doing the olden things. So that is how we are trying to understand our Earth history from the other planets itself. Okay, so these informations was not there. Of course, as I told you, some fossils are there, at Stromatolite or some zircon, some minerals have been found out, but only very few are there evidences. Like we don't have like a strong kind of evidences itself. So that's what we say. Archean era, Hadean era. Hadean era, we have no idea what has happened, how things are there. Very few things are, and of course, Archean era also. Oh, hardly 1 or 2, 3 samples are there, but we don't have anything. Of course, the Proterozoic is documented, because plate tectonics, mountain formations happened during those time. So at least sedimentary rocks came, that layer stratigraphy, at least some informations are there basically. Okay. So that's what they say. So now Earth Archean era. So this is how it has evolved. So in Earth 4.5 billion years ago. Okay. So Earth, because lot of bombardment, temperatures was very high. So its energy production, it was extremely hot actually. Then suddenly radioactive decay started, because when the things form, things will be unstable. Slowly, things becomes stable. So and then so this radioactive decay has happened, and then slowly because radioactive decay, this atmosphere and other things also got formed. So this is a evolutionary history basically, how atmosphere formed on Earth. So initially Earth was also like a stellar atmosphere. Okay, like the cloud molten things are there. Then slowly outgassing came up. Then three, so the condensation we say. So this is the time where proto oceans started formed. The water vapor, which was in the clouds, it started condensing actually, because the temperatures have decreased and oceans started forming, and carbon dioxide, nitrogen, all was there. Then from 3 to 4, so then during that time, I showed you, right, some is a photosynthesis, organic molecules came, anaerobic, aerobic kind of thing. So aerobic is a very famous reaction, because carbon dioxide, water mix, and oxygen gets released into the atmosphere. Okay, so this also started. Then slowly, terrestrial photosynthesis happened. Like photosynthesis, once it comes to ultraviolet, so your plants and other things, that is how things have started. So now this helps us, to understand other planets, whether like Mars is at what stage. If you compare Mars with Earth, say, so Mars also, whether Mars is at here or here or here, so that it helps us to understand our planet also as well as other planets also. So this is what it. So around 4 billion years, so the slow cooling Earth happened. Then rocks crystallized, and then the solid crust formed, and then liquid hydrosphere was there. But then there is a debate basically. Okay, see how water came on Earth. So some people claim that the water was already there, and because of the temperature of Earth reduced, the water were condensed, and then oceans formed actually. But there is also one more theories are there in geology, like hypothesis. So water came to Earth on due to comets. Like last time I told it, comets means they will have full of water and dust kind of thing. So they say that comets have hit Earth, and then the water came from comets. Actually, the water was not the existing on Earth, but it came from comets. That is one hypothesis. Another hypothesis is Earth has already water because of anaerobic, whatever kind of thing. Earth these oceans automatically form. So there are any this we don't know, because all these things belong to that Archean or Hadean, that type of eons itself. Okay. So then the last notable metamorphism, orogeny means mountains basically. Okay, they started this one. Then beginning of Proterozoic Era, this Proterozoic eon basically, magmatic segregation is happened. Continents, say, light rocks enriched in silicon, they started coming. So then ocean began to start. Continent plate tectonics also came into picture actually. So these are collusion set. So initially it was all molten lava, then it got solidified, rocks started, this one, then erosion also occurred, then they collided, and then these mountains and so many things happened basically. So sediments was created, sedimentary rocks formed. Then 3 billion years is a Pre-Cambrian era. Orogenies means mountains basically. Okay, they were created, continental plates came, and then cratons formed. All those things happened during this the Pre-Cambrian era. So one can see this Pre-Cambrian sedimentary series. So in many of our places also, like where do you see most of the Pre-Cambrian rocks? At old ones. Yeah. Of course, some of them you can see on the surface, some of them maybe below the surface itself. So you can identify where are the oldest rocks found on this earth. Where are the oldest rocks? They are found
Africa.
in Africa. You have, then India also. Can you see here? This is just a sketch they have shown here, but you can see below the Deccan Traps also you can see these Pre-Cambrian rocks. You follow? So these rocks you can find out at all these places also, Pre-Cambrian rocks they say. So these some places you can they have escaped the transformation. So this is also a dolomite somewhere in China. So they carbon dated. They found out that they have escaped actually, weathering, whatever was there. But still, the carbon dating shows very they belong to Proterozoic, the ion kind of thing itself. And then once this around 370 million years is there. So this is how the Earth was there. The continents, the proto-ocean was there. This was the thing. Then finally, they started moving, and then they became one continent. They also call this the Pangaea or Rhodina. Some names they have given, and slowly so this was a 220 million years ago. Then at 130 million years ago, this was happened. Then 70 million years ago, and the Miocene, that is the current age, the 10 million years ago, this started forming into picture also. So this also happened. You see, 1, 2, 3, 3, 4, and then 5. That is how all the continents evolved, and the plate movements and other things also happened. So that's what they say. So now in our Mesozoic era, that is Mesozoic, 65 million years ago. Okay. So this era, you see, climatic fluctuations has happened. Climate becomes, and then we started oceanic life also. Ammonites, they are formed basically at the Mesozoic era itself. I will just show you one ammonite. Okay. Yeah. So can you see this? I will just show you one rock. Is it visible, all of you?
Yes, sir.
What is this? You can see any peculiar thing? This is a rock basically. It is a fossil of some ocean life. What do you call this? Any of you have any idea? This or even this itself. If you have come here, no, our lab has. Okay. So this also you can see. This is also a fossil basically. You can see here, visible.
Yes, sir.
So what is this?
Sir, looks like a shell.
Looks like a
Shell.
Shen only followed. This is also like that fossil, 65 million years old. This belongs to the Mesozoic era. Okay, these are the fossils actually. So the rock will be like this. You followed. See, the rock will be like this. If you see here, it is like a rock only. You understand? So it will be a rock. So if you remove this and if you cut it, you will see inside these type of fossils actually. You follow? So this is an ammonite fossil, 65 million years old. You understand? What do you call this in our Puranas? Any of you have any idea? What do you call these type of rocks?
The Shaligram.
Shaligram. Excellent. Who told this? Kshitij.
Yes, sir.
Oh, very good. I see. You have, how do you know? Like you already seen?
Yes, sir, I have some of these in my house.
Oh, okay. People also worship you followed, right?
Yes, sir.
But what are these shaligrams? They are all ammonite shells, actually. The oceanic life. Where do you find the shaligrams? These ammonite shells. You know which place we get these type of things in our India? Of course, India we don't get. We get these things from Nepal. You know that Gandaki river has. Even in Europe also many places. You know we find out. But anyway, of course, Indians. You know we worship these shaligrams also. So sometimes what like some people say, like our Indians say, we worship the oldest kind of thing because these shaligramas are almost 65 million years old. Very old type of rocks. These are not rocks, are fossils basically. Okay, so that's what they say. So 65 million years. So that's what we are calling this as these saligramas. Okay, that ammonite shells actually. Variety things are there. So this they did around Mesozoic era. So Mesozoic era means where was our India? So if you see this, so Mesozoic means 70 million years ago. That is a number four. So four was here basically. Okay, then five is four was here, and then five was here. So Mesozoic era means where was the saligram, as you can see here, 70 million years basically, Cretaceous time. Then 65 million years is this saligramas. Okay, so you can see they were all lying in this place, and then India collided with this Eurasia, right? Due to that, some of these fossils that ocean got disappeared and they got stored in the rocks itself, and that is how we got these ammonites. Okay, so 65 million years. Okay, so this also I think Kshitij has, so you are worshipping gods, of 65 million years old itself. So anyway, that is one thing. That now here, this is what I told you. So like around 66 million years, say, I showed you in the geological graph also. So this was a very important thing around 66 million years ago. Okay, so this is Cretaceous, Mesozoic to Cenozoic. So that is a dinosaur time. How this happened actually? So there were two theories are there, hypotheses. As I told, right, in geology we have a hypothesis. So large meteorite impact actually. So this was one hypothesis given by some group of geologists, and then intense volcanic activity. Our Deccan Traps also belong to the same time. So they say that there was a huge volcanism all over the earth. So that was the reason why these dinosaurs or whatever, it vanished around our earth itself. So the reason for this is iridium actually. Okay, so this was the element they found out, at the time of extinction. So they said meteorites also have a lot of, iridium basically. Then volcanic activity also they found out this element. So now whether this or this, we are unable to conclude. So there are a lot of papers published on first hypothesis. There are also papers which have been published on the second hypothesis also. So where this impact occurred, any of you have an idea where this meteorite impact which wiped out the dinosaurs, where this meteorite impact was? Or any of you have any idea? So where was this meteorite impact which wiped out the dinosaurs? So that is near. You can see this, read this place. Chicxulub crater actually. It is in Gulf of that Mexico, somewhere in this Yucatan Peninsula. So they identified a huge crater. So then they back calculated actually what will be the asteroid shape or what should be the asteroid type and this one, and they simulated basically, and they said that this material, this impact, say, wiped out, to all the dinosaurs also. And of course, volcanic activity is also another hypothesis. We don't know, like both of them they have their own reasonings and other things also. So anyway, so that is how it happened. Now after this eras, then we have tertiary era, that is from 65 million years to 1.8. That is ammonites I showed you at 65. Then this one say. Then we had intense tectonic activity, plate migration happened because India was not part of this one, So India collided with Eurasia, and all of these the Himalayas got formed, and we started getting all these fossils and other things also happened. Then after tertiary, so the next one is a quaternary era. That is what we are all of us are sitting at. So the quaternary era. So quaternary era, basically the boundary between tertiary and quaternary is this glaciations, they say. So glaciations means huge ice sheets actually. So they started forming in Antarctica, that ice age or something like that, they say. So that creates the boundary between tertiary and the quaternary. So our quaternary era, that is where we are all of us are living. So that is glaciations basically. Okay, that's a huge ice sheets got formed in Antarctica, something like that. But now people are saying that ice is also melting. So now we have to give another geological the thing itself. Okay, so this also some theories. So anyway, so if you want to compare, all of them, all the geological time scale in 1 year times, a metaphor kind of a thing, analogy kind of a thing. If you see, if you want to club everything in 1 year, the whole Earth, if you want to explain in 1 year, so one geologist have try to explain. Like if we say on January 1st, say solar system Earth was born actually 4.5 billion years, and then January 4th, Moon has formed actually. Okay, then January 2nd, say the oldest known mineral grain, zircon, that I showed you, right? That zircon grain, which was found on Earth 4.4 billion years. Then February 13th, say, so oldest known rock, the gneiss has been found out. Then March 1st, chemical evidence for life came into picture. So this is the place where, what is that chemical evidence? What is the name of that one I showed you long back? Microbe. Do you remember?
Hemolites.
Hmm. So this was the one Stromatolite actually. So this was came into that time. Okay. So if you club that also, and then if you put so this was Stromatolite. Then oldest known fossils actually. This also found out in Australia. Then June 14 said the Stromatolites only increased the atmosphere oxygen. Okay. So that's a 2.5 billion years. Then August 25 say oldest complex shells. Then November 13 say animal fossils, 600 million years we have. Then major diversification of animals is a Cambrian explosion started 540 million years. Then November 26th, the oldest terrestrial fossil fungus we saw. Then December 3rd, say tetrapod. Then worst mass extinction actually 250 million years. So this was one worst mass extinction happened. 90% got vanished from Earth itself. Then December 12th, say oldest known dinosaur fossil. Then supercontinent of Pangaea. Okay. So this December 13th, oldest known mammal fossils, then flowering plants and extinction of dinosaurs. So 65 million years ago, I told you, right, there was Cyclops crater or volcanism, December 26th. Then December 31st. So we are just putting all these geological events in 1 year kind of format, say, taking into account like normalization of this one. So December 31st to 12:25 p.m. basically. Human chimpanzee these diverges, and then 11:25 say Homo sapiens, then domestication of dog, and then 11:59, 22 seconds oldest writing has been found out. Then Great Pyramid of Giza, so it has been built in December 31st, 11:59. From compare from the 1st January, pyramid was established. Then Copernican revolution happened. Then the Darwinian theory says so 11:59 seconds basically. So now we are living. So if you compare the life of Earth and then our human life, say how much we are compared to the whole thing. See, we are trying to fit the whole geological time scale in 1 year, say. This is what it happens actually. So in the whole history of Earth, where are human beings basically? Now, what is our if you 365 days, if you give the human beings how much it is? What is our comparison to that?
Half day.
Half day. See, December 31st, 12:25 p.m. humans and chimpanzees have diverged basically 11:25. Then if you compare our industrial revolutions, if you compare with how much is industrial revolution compared to the older one, compared to the entire life, geological life, hardly. See, Copernican revolution, what's the time between Copernican and Darwin, this theory? when you compare with the history of Earth, how much is the time difference? No.
2 seconds.
2 seconds actually.
Seconds.
So now what is your life then compared to, we are talking, right? We are so great and we are this and we are that or so much. So when you compare yourself with the history of Earth, say what is our life? How much duration is our life when you compare to the geological history of Earth?
35 minutes.
Minutes, sir. No.
Yes.
Human. I am talking about your life. Not the whole human beings, our life when you compare with this one. So human beings itself is 35 minutes, say. And in that, what is our life? How much is the duration of our life when you compare with the geological history of Earth? Hardly it is.
0.1 second.
That is that much only. In that also, if you put your age or whatever, so you can see. So when you compare this entire thing, we are just nothing actual. So we are just like, you see, blink of an eye or something like that. That is what you see. They tell. That is, beautifully. This some person he prepared in Google internet. I searched so nicely. They made actual the whole geological time history in 1 year. He tried to explain so nicely, this information. So now we don't know how many years. See, Earth is, if you take 365 days, say, we have information about how many months. Nah. So we have information only on. So only, we know only about in the month of December, basically. So we may have, of course, December 31st, we will have more information because in human, chimpanzee, all those things are there. Lot of fossils we can get on one day. You follow 365 days. Now, if you go this one, so maybe the month of December, so in our 12 months, only we know exact history of 1 month. So like 12 chapters are there, say, detailed information on even one day, or maybe you follow, right? 1 month only we know the information actually. More than 1 month, so we don't have much information. We have little bit, 1 or 2, 3 fossils, but this the whole information. So January 1st to November, we don't have much fossils or much detailed information to know the history of our Earth itself. Okay, so it is a very nicely, this put it out in our geological time scale in 1 year. To explain, what is the importance of geology or how much information, say, we know about our planet Earth. Okay, so it's very important. Now, similarly, say these geological time scales. Now, people started. I showed you the geological time scale on Earth actually, but the planetary geology, you have to construct these type of time scales also on other planets also. Like other planets, how do they construct? Like for example, Moon. Say if we want to construct a geological time scale, okay. In Earth, the geological timescales we have constructed, the boundaries have been constructed based on some huge, the geological formations are huge geological things like mass extinctions or maybe, the ages of the rocks or whatever, based on that we have decided actually, okay. But now if you see Moon, at least anyway, Moon people have gone there and brought rocks or whatever, but still, and of course Mars, nobody has gone till date, or Venus, or, this Mercury or other places. You don't have much idea. So now in planetary things, say, like in Moon, how did they arrive? Can anybody have an idea? How did they, these geological boundaries, say, how did they get this one? No. So these geological boundaries, say, we don't have much information on Moon, like, the major geological processes. Okay, and anyway, these fossils also are not there. So this geological time scale, the boundaries basically, they have been made from the craters actually. Okay. So like this, the Moon, people have gone there, got samples, lot of remote sensing. Anyway, we are also going to do after some point of a time. So all these things to say. So they have estimated the ages of all these craters. So they found out that this is the Nectarian crater. Somewhere it will be there, Mare Nectaris actually. So they found out all the craters and found out that this Nectaris crater, this is the oldest crater, on the Moon basically. So from the Nectaris time, they had a huge gap actually. Then the next thing what they found out was this Mare Imbrium, this huge crater you can see here. So this is the next one formed basically. So like that, they formed, they gave names for also. So this is a Moon geological scale given by some 3 scientists. So you can say pre-Nectarian scale. So then you have Upper Imbrium actually. Imbrium. So these are all crater names, they have given. Then Eratosthenian crater. So this is also somewhere, copper, somewhere it will be there, this crater also. So based on all these crater ages, So they have classified. So here we don't have information like Earth, you have a fossils, you have a lot of informations are not there for other planets, but for moon, say, so just based on moon or Mars or whatever, just based on the craters itself. Okay, we will be doing, I will explain you how they do these things also. So based on this, they divide the major geological things on moon also. And the recent thing what they found out on moon are Copernican basically. Okay, so Copernicus is also a crater. So where is the Copernicus? Can you see here Copernicus crater? This portion. All of you can see. Is it visible? This is a, you can see the Copernicus. So this is the one. Now these people, geologists, we will see in remote this one also. The ages of the crater they estimate. So whenever the crater is formed, say, okay. So when there is an impact, basically, what happens if it is a huge meteorite impact? The material flies off actually. So when the material flies off, say, they will see these type of radial lines. So you can see this is a Tycho crater. You can see here Tycho, which is located here. It is very bright around this crater. Say, can you see a lot of radial lines? That white color lines, can you see? Even Copernicus also has some type of radial lines, but they are not that bright as Tycho crater. You can see right near the Tycho crater, full white color. So many radial lines are there from this crater. Can all of you can see?
Yes, sir.
Yeah. So they say that if you see these radial lines, say, and if it is very, when you see the image processing, if it is very bright, this one say, so that means that crater has formed fresh actually. You followed. So based on that, they estimate the age. Of course, we also will see in the next class, maybe next week, and I will tell you how to date the craters. Now, when you see this Mare Imbrium, say, or this Mare Nectaris, basically, so this is a crater actually. Okay. So this one, if you see, it is not that bright actually. Then the radial lines also have slowly, disappeared. Okay, because of some other meteorite impacts occurred or whatever it may be. So the youngest they say right, the youngest crater they identify based on these radial lines, and then the bright, that color will be there, and we will see after some point of a time. So you can see. So the Tycho is one of the now people are studying this crater because it's very freshly formed. Fresh means not last year or something, some million years ago. Okay, so people are trying to estimate, how this age formed like this also. So this Mare Imbrium, this is also very wide. It's a huge crater actually here. Okay, so I will show you in the next class also some more images, and then how do they find out the date basically when this crater has formed or something like that also. So these craters is so the age of these craters, and based on that they decide the age of the craters, and then they have done all the classification, and based on that classification, say based on the craters, they have divided this moon into 1, 2, 3, 4, 5 geological periods, like pre-Nectarian, then Nectarian, then they have early Imbrium, late Imbrium, Erastonian, then Copernican craters itself. Okay, so these are based on the craters only. Now, similarly, Mars, if you see, so Mars has some atmosphere also, So they divided this into based on craters and volcanic activity. Of course, I will tell you more information in the next class. So they have divided early Noachian, then late Hesperian, Noachian, Hesperian, Amazonian period, then middle Amazonian period, and the late Amazonian period, and then Venus also. So we don't have more information because no rover or nothing has happened. So they divide this into 3 geological ages. Of course, these are all very a preliminary kind of thing. Once we get more information, say once missions goes, like we will get more number of samples and then carbon dating, then maybe we may be able to give some nice geological process actually. Okay, and this is our Earth process, the geological things which we have already discussed: Pre-Cambrian, Cambrian, Hadean eon, Archean, Proterozoic, and then Phanerozoic eons itself. So now what is the main interest of geologists is like Earth's Hadean era, say. So here we don't have any information basically. So now this you may get the information about this era from some other planets actually, maybe from Venus, or maybe from Moon, or maybe something else also, or the Archean era, say, and Earth corresponds to which era on Mars, Mars. So that is very important. They're comparing the geological time scales, so we can find out actually where we are in our solar system, so where we are going to forward or backward or whatever. So a lot of information we can do from this planetary geology itself. Okay. So these for the moon, I already showed you. Like moon, as already we said, right? These are all only tentative. There is nothing like fixed. So there are some 3 papers that people have published, like you see, they have done some, but these are all based only on craters, only the age of the craters, that brightness, that also from the remote sensing, and the rocks have been brought up by the Apollo missions, so they have done carbon dating also. They have divided it into this one. So this person said, like, the rider, he says, more or less same he says, but Erastasian, he puts at 1.5, others put at 1.1. So there are some debates going on actually, where what we have to form. Maybe in the future, 10-25 years, these things may get more clarity. Okay, so I will stop here. So if you have any questions, you can ask me. So I will send you this lecture.